All right. Hello, and welcome to Lecture 7, the much awaited. This one took a bit of time to get up, so I apologize for that. Also, new microphone, so hopefully the sound's a little bit better. So, yeah, I'm actually really excited about this particular lecture. This is where I'm spending a lot of my time right now, specifically in generative modeling using unsupervised learning techniques. In this lecture, we're going to get into some math, but keep in mind that it's really more about you understanding the general concepts, and it's not necessary to sort of really get all of this stuff at once. Although I would, given that the sort of projects are probably on your mind, for the final project, a lot of the stuff in this particular lecture may be really interesting for a final project, just implementing one of the models or exploring one of the papers. Because, for example, we'll talk about generative adversarial networks. we'll also talk about autoregressive models, both of which have really interesting applications for game development. And throughout this particular lecture, I think the real topic of this seminar is really going to come out in the sense that this is where you may see the most direct applicability to games and simulation. Maybe less so in simulation, but even so, right? Generative models are a terrific approach when, say, you don't have a very large data set. And so, if you think about simulation as a way to augment your existing data set, generative models are another way to augment your existing data set as well. So, the combination of simulation, generative models, and supervised learning, a lot of things can be solved. And there's a lot of overlap as you dig into generative models and the underlying theory. There's a lot of overlap with how a lot of reinforcement learning is done as well, in particular the sort of variational lower bound, as we'll talk about it, and how that's seen in particular in Q learning, or using deep neural networks to approximate Q functions and policy functions. So we'll talk about that in the remainder of the course. I won't get too deep into that, and I might have just sort of misspoke about it, so don't worry about it too much. But with that, let's jump in. And so, like, what is a generative model? Why does this sort of require special treatment? Because most of the last lecture we talked about unsupervised learning and some of the things that you can do with it. And while generative models are a form of unsupervised learning, why are they so special, and why do we even care about them? So to go into it, right, as we talked about last time, we are living in a world where we're seeing data being presented to us, and there's no real structure around that data. So we have a bunch of different observable data, and by the way, this is where a lot of the reinforcement learning loop-in comes in, as we'll talk about in the next lectures on that subject. But essentially, we have a bunch of data that we're seeing, and we'd like to determine a distribution that tries to match the distribution of the data that we're seeing. We do this, as we mentioned many times now, with something like a max likelihood model, but ultimately, the actual data probability distribution is a very complex function, right? And so we can approximate it with a function approximator, as we've seen with deep neural networks, where such that, right, given a probability distribution parameterized by theta with a input of z given by its own prior distribution p of z, which we'll talk about more what that means and why do we care about separating the probability distribution of the data with the probability distribution of our what's called the prior distribution. But say we have that, we can now approximate it and try to minimize the observable difference between the probability of the data, or p data, and this respective p of probability distribution as parameterized by theta for this value of z that we're randomly generating. Said in a little bit of a different language, which is, I know that's very heavy and kind of formal, right? Ultimately, imagine we have some kind of probability distribution that matches our data distribution, right? But then how do we sample it? We can't just sort of sample it with the same value, right? We're going to somehow sample a distribution. And the way you do that, right, is you have some type of variable that then samples that distribution, right? with like a random number generator. For example, if you were to use a random number generator, right, and then determine the probability of that particular number given p of theta, probability distribution is parameterized by theta, right? That's like basically saying a uniform distribution, right? Because if you were just sort of choosing a number between 0 and 100 with equal probability, right, and then plugging that number into this probability parameterized by theta, then that's like z is now part of a uniform distribution. So there is this sort of hidden thing there. Even if you're doing this with a computer with a random number generator, your random number generator ideally is a uniform distribution. But we could use other distributions, right? Say we know something about that sort of distribution of values, like we expect more values around this particular mean. If we know that, right? For example, in the case of images, and I know that it's a bit of a stretch, but if we know that we are more interested in pictures of cats, right, we can try to sort of model that prior distribution is something that sort of looks like cats. And you'll see a little bit of that in this lecture as we go through this at kind of a high level. So this is sort of the general idea behind generative models. We want to have some kind of variable that then is able to be plugged into this distribution that we've learned, and then we want to maximize the likelihood of that distribution compared to the data that we see. And we'll see a couple of different approaches to doing that. But what at the core of this is we're really trying to learn that underlying probability distribution in a way that is tractable, in a way that we could then manipulate, either by feeding it values, such as with z, or we'll see actually a different kind of model that sort of avoids that whole problem entirely. But before we go into it, let's kind of dive into let's kind of recall maximum likelihood models. We've talked about this a few times now in these lectures, right? And so ultimately, with a maximum likelihood model, what we're trying to do is we're trying to maximize the likelihood that the data that we see is coming from a probability distribution that we've defined. And if we can maximize that, as I've shown this image like 3 times now, we ultimately, you can see different probability distributions will result in different outputs. And like, for example, in the case of this particular image down here on the right, we can see that the blue curve would maximize the values given in these blue values, whereas red may seem like it's a bit more accurate in terms of the mean, but you can see this value over here has no probability distribution practically, and here as well, whereas in the blue we have a much sort of more maximized value. So if we were to take each one of these values and then equivalently map them to the blue to the y, and then sum them, that sum would be higher than if we were to do the same thing with the respective red curve. Now, one of the things that we'd like to do, so we can do this with just the probability distribution, but it's a little bit easier to deal with the logarithm of the distribution, as we'll see in a lot of cases in this particular lecture why that is. And often instead of maximizing, we minimize, but this is largely just a sort of convention thing, right? You can do the gradient ascent or you can do gradient descent. It doesn't really matter. Ultimately, if we could maximize the log probability or we can minimize the negative log probability. Often you'll even take the mean of this value, but it depends on sort of your use case, how sensitive you want your this negative log likelihood function. So again, the intuition here being that if we can maximize the likelihood that the data that we saw came from the distribution that we've defined, then this distribution matches well the underlying data distribution of the data where it's coming from. Another way to think about this is in the context of Kolmogorov complexity, right? If we can somehow define a program, a language, a model, whatever, if we can somehow design a system that can output the data that we're seeing, then we have essentially sort of compressed that down to a program that can produce that data. And so you can kind of think about it from that perspective as well, where this probability distribution sort of encodes the Kolmogorov, like it essentially minimizes the Kolmogorov complexity of the data that we're seeing, right? So in the case of Kolmogorov complexity maximized, where with just a copy of our data, right? The probability distribution or this model that we're trying to learn is trying to minimize that. I mean, we're trying to come up with a system or the set of rules that outputs our data with the minimum complexity as possible. So that's a different kind of take on it if you're familiar with that line of thinking. But in that sense, unsupervised learning is a lot closer to information theory and that kind of stuff versus supervised learning, which is a little bit more, just aligned with just general, linear algebra and that kind of thing. So cool. This is a bit of a got to twist your brain a little bit to kind of think about these things. But it's very, very powerful. So I think we might have talked about this particular model already. And I'm going to be referring to slides from this class, CS294 from Berkeley. It's taught by Peter Abil. So I do recommend checking it out. It does go into a much deeper depth on some of the subjects that I'm talking about. I'm going to move myself around so I don't block the equations here. And I'll also be referring a lot to the Stanford CS231N lectures as well, which I've also included links to very easily here. So not everything's from there, but definitely if you're interested in a much deeper dive into a lot of these subjects, you can find a lot more materials there. So I'm going to kind of do my best to cover a lot of subjects in this one lecture. At a level where hopefully it'll pique your interest, but maybe not necessarily scare you away with a ton and ton of math. So let's talk a little bit about this mixture of Gaussians or logistics, but let's talk about Gaussians in particular. One way for us to sort of treat the data that we see, this probability distribution that we're trying to learn, is by combining a number of different probability distributions that we know, for example, a Gaussian or a logistic. So you can see down here in the bottom right, the P of theta is parameterized, where theta is essentially going to be these values of weights, the means, and the standard deviations of a particular normal distribution, and then we sum them all up. So you can have 3 or more combinations. As you can see up here in the top right, we have 3 kind of combinations of different things. We've seen this for the purposes of clustering. So now if you do this, you can in theory try to determine where your modes are. So that is one approach here. But more generally speaking, if we can maximize this probability distribution where these weights are all equal to 1 in total, so each one of them is less, so you can kind of scale them up and down. That way we can ensure that our overall probability distribution, the sum, the density, is going to be equal to 1 over the span of the distribution. And then we just plug it into our negative log likelihood. So if we can do this, and we can then figure out which way to change all of these parameters, and we can just do this through PyTorch or whatever AutoGrad solution that you want. And then we can essentially match the distribution. As you can kind of see on this left here, this is actually out of this class CS294, where a bunch of data has been mapped to this learned distribution, and you can very easily see this learned distribution is essentially a combination of Gaussians. Now, the issue with this is it's good for low dimensional data. As you can see, it does quite well. But you can imagine that it doesn't do as well with high frequency changes, especially because the Gaussian is going to do very well in certain ways, but it's not going to do well when you have a lot of perturbations. It's kind of going to even things out. And as a result of that, for natural signals like images, as you can see in this bottom left corner, this image out of Peter Abil's course, when you apply this to a image, that tends to sort of demonstrate a lot of very quick changes in frequency, we don't get a particularly great result. So I'm not sure how many Gaussian mixtures this is. I think from the class it was like 4 or 5, but you can see there's a lot of issues here. So the mixture of Gaussians does do well, and it's a great kind of mental model for us. But ultimately, once we get to more complex dimensionality and more complex signals, in particular natural signals, which don't unfortunately look like normal distributions as often as we'd want them to, we start to kind of need something a bit more expressive. So our model is not too expressive. I think one of the intuitions that I have, and like keep in mind, take this with a bit of salt because I'm still figuring a lot of this stuff out as well. But one of the reasons that natural signals don't do well with a mixture of Gaussians is because a particular pixel in an image right, is not the value of that pixel is not going to be described by a process that is very Gaussian-like or very distribution-like. In fact, if you know this is a deep learning for games, so if you're familiar with the rendering equation is really going to have a hard time dealing with this sort of normal distribution. And as we know, right, if you've seen that MC Escher image of him holding the sphere, right, every pixel, every light that we see, to truly calculate the value of the light hitting a camera at a particular point, you need to basically know everything about the universe at that very moment, right? Because the light has been produced by who knows what and a ton of previous information, right? And so a lot of assumptions are broken in terms of being able to apply this kind of model to a thing. In other words, what I'm really trying to say here is that underlying distribution that we're learning can be exceptionally complex. But the good news is that that's why we have neural networks, and that's what deep learning is particularly good at, is approximating a intractable and very, very difficult to express function. So let's take a little bit of a look at what options do we have, right? Like let's not worry about what we can't do. So this is actually again from the CS231 lecture on generative models. I really highly recommend, if this is something of interest, that you all check it out. Definitely a lot of things have been heavily borrowed and kind of applied from there, and I took that course as well. It's a terrific course, so just in general, a lot of really good assignments and things that for you all to kind of dig into. But let's kind of talk about it. So the mixture of Gaussian logistics is an example of an explicit tractable generative model. So there are a lot of different kind of approaches here. We have the explicit approach, and by explicit we mean we're explicitly calculating a probability distribution. And within explicit distribution, the explicit densities, we have two different ways. We can approximate the density by way of variational lower bound, as we'll talk about in variational autoencoders in a minute, or tractable densities. And tractable densities kind of akin to Bayes nets or combinations or flows, and we'll talk about a couple of those in this lecture as well. So in the case of a mixture of Gaussian, we're actually dealing with a tractable density, right, where each value is a tractable combination of Gaussian mixture, a mixture of Gaussians. But as you saw, it's not sufficiently expressive. Maybe if you do like thousands of Gaussians, but at that point, maybe there's a better way. So that's the explicit density. You're either approximating or you're directly kind of trying to discover this thing. An alternative is implicit density. And in implicit density, what we're doing is we're avoiding max likelihood altogether. We're basically kind of approaching this either in a Markov chain, which is sort of similar to what reinforcement learning is doing, and there's also Gibbs sampling and Hamiltonian sampling, but we're not going to talk about that in this lecture. So if that's of interest, please let me know, and I can put together a lecture for that as well. But the more direct approach to implicit density approximation or determination is what's called a generative adversarial network, which we'll spend a fair bit of this lecture talking about. So to start, let's talk about explicit density models and kind of talk about what is meant there exactly. So in an explicit density model, again, we're really just trying to determine the probability distribution parameterized by theta directly. And in this case, what we're going to say is that each dimension in our data is going to be conditioned on the previous dimensions. And so what that means is the probability of our x is going to be equal to this sort of product of the probability of every variable given the variables that came before it. It's sort of this sort of like, big dog pile, right? Like the first variable that shows up, we have a probability distribution for it. Great. Now the second one, we just apply that same distribution but conditioned on previous values, and just rinse and repeat until forever. And that way you can reconstruct, or you can basically determine how likely a particular x is. And if you can do that, right, if you can determine what that probability distribution is, all right, you can kind of run this in reverse, essentially. Well, not really reverse, and I'll talk about how different models do it. But for example, I can put in a value and then run it again and get the next value, and run it again and get the next value, and so on and so forth. So one of the downsides of explicit density models of this nature is that they take up a lot of time in sampling. So because you're sampling one dimension at a time, one value at a time. While in training, it's also kind of it's also a little bit slow, but in theory, because you know all of these values, you could do them in parallel. So explicit density function models tend to be faster at training and slower at sampling. There is a way to invert this such that it's fast at sampling and slow at training by basically doing the opposite approach. This is true for flow models in particular, but we're gonna that's kind of out of scope of this. So now here is one of the places where you really see this benefit of the applying a log. Now, if we take the log likelihood, remember we just want to try to calculate the negative log likelihood of a particular sample X. Instead of having to do the product, we can just sum them together, which is just an easier computational thing to do. So one of the benefits of using log here is that it turns a product into a sum. So we've already seen one of these models. That's a mixture of Gaussian is exactly that, right? Where we have you could do each one individually, but really if you have multiple dimensions, so the 2D case of mixture of Gaussians, you would then calculate your value of x and then use that value to then condition the second dimension of your problem or your thing. So that's one thing that we've already seen this kind of in action just in this lecture. We've also seen this in recurrent neural networks. And in recurrent neural networks, as we talked about a little bit in that lecture, right, you can kind of think as your next output being conditioned on the previous inputs on your network. And so you have this sort of probability distribution as parameterized by the network itself as being a conditional on every variable and every value that you've seen before. So we treat this as a time step, and then back propagating it through time, but it's the same general idea. And so that's sort of the idea here, is like where we're basically conditioning the output, this particular value on the probability of this particular dimension on the previous dimensions seen so far. How you do this, there's a lot of different ways how you do this, right? You can kind of randomly choose it. You can kind of go about it what's called kind of autoregressively, and even in autoregressive models, there are different ones. We're not going to talk about MADE or NADE, so if that's something of interest to you all, let me know. I'm happy to talk about it a little bit more. But one of the models we will talk about is Pixel RNN and CNN. So this is by Aaron van der Oord. It was published in 2016. I highly recommend checking out this paper. It's a really good paper. It's very interesting. It proposes both Pixel RNN and CNN. In the case of Pixel RNN, it's literally applying that thing we just said, except for pixel values. So instead of a recurrent neural network that's being applied to words, what we're doing is we're applying it to pixels in an image. And you can kind of see there's a number of different approaches that can be taken here. So for example, in the row LSTM, you can kind of see the approach that was being taken where each value is based on these previous ones, and you kind of have to sample this in a particularly complex way. So to actually accomplish this is pretty hard, and I haven't implemented this particular model, but it's a very interesting one to kind of read about and understand. Alternatively, you can accomplish this almost directly with what's called the pixel CNN. And so what's nice is given a particular convolution, right, the convolution in a way determines which values a particular output is going to be based on. So what you can do is you can mask these values. So as you can see here in this red pixel, this red pixel is being conditioned only on the basically top left value. So if you start in the top left of the image and you go, you're essentially guaranteed that the output on the value of that pixel, the probability distribution is being learned only based on the values that were previously kind of seen or calculated by the model. And now you run this convolution over your entire image. And at training time, what you're doing is you're essentially maximizing the likelihood of this. So you're going to basically run that mass convolution, right? And then figure out the distribution output and maximize that. And then you have the probability distribution as represented by your thing that you're going to maximize by way of, or minimize the negative log likelihood by way of your autograd. And then at sample time, what you do is you basically plug and chug a value into the top left pixel. Then you plug that into your model, and then it'll give you a probability distribution for the next pixel, which you then sample. That sampling then gives you that next pixel. You put it into your buffer, into your image, and then you rinse repeat for every pixel in your image. So you can kind of see, again, we have this problem of relatively fast at training time because you can, in theory, do this operation for each pixel independently of the others because you can do this convolution in parallel. It's only depending on the input, and but then at sampling time, you have to sample. You need the previous value of x to determine the next value of x, or the next pixel, and so it can be quite slow. Now, Pixel CNN, and this is beyond the sort of scope of this particular lecture, has a problem, right? For example, this pixel in an image, it kind of sucks that like we can only look up and to the left. It doesn't quite make sense. Images in real life don't work that way. So there are limitations, not to mention there's also a blind spot problem. As you can see here, this particular pixel is not going to see these pixels to the right of it, right? And it kind of creates this diagonal. So for example, the pixel on the left here in this image, on the beginning of this line, is going to be missing that entire triangular portion of pixels that have already been run through. Which is sort of a bummer. So there are techniques to improve this in terms of just dealing with the pixels that you've already seen. There are techniques also. What you do is you can kind of do a small resolution image and then scale it up. But this is definitely kind of an area of research. You can imagine that this is very powerful for images, and in fact it is. But it also is very powerful for audio. And so WaveNet, which is based on a very similar concept, except with only 1D convolutions, can actually be used to create and to do state-of-the-art audio as well. Actually, let me try to pull this up because I think it's very, very impactful. And in particular for deep learning for games, this is one of those very interesting applications. Let me pause while I bring up the website. Okay, cool. So, whoops, here we go. So this is the WaveNet page out of DeepMind. So as you can see, it utilizes a very similar concept to this sort of masked autoregressive model that we've been talking about in 1D. It also utilizes this concept of dilated convolution. So instead of looking at just the values next to it, it looks sort of with this dilation. And the reason for that is it increases the respective the receptive field. And as you can see in this particular animation very well, right, you can see how each value is being determined. So we do this thing, we now get this value, we plug it in, and we rinse repeat forever. This is the case of sampling. And in this case, the dilated convolution allows you to have a receptive field going back a ways. In fact, their maximum receptive field dilation, I think, is 512 in the paper, which suggests that it's a total of, I believe, 1,000 samples receptive field, which kind of, given the sampling frequency that they're using, I think is on the order of 200-300 milliseconds, which gives them sort of just enough time to make sense of the audio before to reconstruct audio and interesting things like that. So this was actually a really big deal when it came out in 2016. I'll try to kind of play a couple of examples, and hopefully I don't blow up the audio here. But this is an example of parametric, text-to-speech. This is going to sound quite robotic. I'm sure you all have kind of recognized this from like Siri and what have you. But this is sort of what it sounds like. So you can hear it's a bit robotic, it's a bit choppy, kind of tinny. So WaveNet really made a huge leap, and if you listen to this, it sounds a lot more like natural speech. It's also able to do this with Mandarin as well. And what's interesting about this, so they ran the model, the way that they do the text to speech is they actually condition it based on, words and text and stuff like that. But they can also run the network without giving it any conditioning at all. They just, train it on a corpus of audio. and then see what comes out. And in this case, you can hear this produces what sounds like natural speech, but has no real speech in there. And you can, as I'll go through these samples, you'll hear different sort of almost languages, but they're not really languages. And this is actually, when I listen to this, I think a lot about the game The Sims, where they're all speaking this language, and it almost like has a language to it, but it's like gibberish. But there's something about it. There's like a, they're definitely saying, and obviously that was all scripted. But in this case, you could actually create a language for a video game that's not really a language. I think that last one's probably German. Um, you can also get the fun things. You can get some, this network to say the same thing in different voices, so that's very valuable. One of the really cool applications is applying this to music. So this was a network that was trained on a corpus of classical piano music, and not conditioned on anything, and so it kind of just sounds like whatever. So you can see this is a very powerful technique. In fact, if you're really interested in generative audio, one of them, we're not going to talk about it too much in this lecture, but based on VQVAE, OpenAI came out with Jukebox recently, which can actually produce entire songs, which maybe I'll bring up in the rest of this lecture. But very, very, very cool, and you can really see the connection with some of the things you might do in games and simulation. Finally, I think the most interesting applications of machine learning or deep learning to games really pops out in this generative, unsupervised side of the house. Uh, Also in reinforcement learning, as we'll talk about, which kind of shares a lot of things with it. So yeah, autoregressive models, in particular Pixel CNN, RNN, and so on, are very powerful and can be used for a lot of really fun applications. But like I said, they have a limitation in that they take a really long time to sample from. So you kind of have to make that consideration as well, although there are some techniques to improve on that. So the next sort of model that I want to bring up in unsupervised learning is also an explicit density model that is, tractably calculating the distribution directly. It's what's called a flow model. And the flow model essentially leverages this idea of change of variables, where it takes the probability distribution of x and then changes it into, by way of this flow, which then, you kind of scale out this probability distribution by the essential determinant of the Jacobian. What this is a much. Maybe I can move my guy here. Um, I'll just go off. I'll just go over here for now. But the idea being that you're taking a particular function and you're mapping this x value into that function, then you're applying that expansion and that change. The key to making this work, though, is that that function that you're using has to be invertible and it has to be differentiable. Why does it have to be invertible? Because what we're doing is we're going from our value x and then we're moving into this value z by way of this value of this function f. And by doing so, we're changing the space. We're going from x to z. By the way, x and z in this case are the same volume. They're the same. Sorry, they're the same dimensions. So what we're doing is we're transforming x into z. But for this to work well, we want to have a function that can take us from z back to x. So this function has to be both invertible and it has to be differentiable, because we need this determinant, and hopefully we can take the determinant relatively easily, which we'll talk a little bit about as well in just a moment. And so this probability distribution of x, what we're trying to maximize now, again, this is a max likelihood model, is simply going to be equal to the probability distribution, this parameter bi of this function, and multiplied by the determinant of that Jacobian of that function. So if we can do that, if we can maximize this particular probability distribution, now we get to a mapping of x to z such that the z, the latent variable, can be then moved back into x. And why is this interesting? Well, we have a bunch of, remember kind of the construct of the unsupervised learning problem, right? We have a lot of x's and we have a lot of data, but it has no structure. We're trying to learn structure, right? So if we can learn this function that takes x to z and then maximizes the likelihood of that particular distribution, right? Now we have this variable z, which has its own distribution, right? So I guess one of the missing bits here that I didn't include is this probability distribution is the probability distribution of z. Probability distribution of z is some kind of prior distribution, just like we were talking about before in terms of a normal or a uniform distribution, right? So what we're going to do is we're going to go x to z, and now z exists in this other distribution, and now we can go from that distribution back into x. So what we can do now is now we can sample that distribution. Now we can basically go through the z distribution and then map each value of z directly to a value of x, including values of x that we have not seen. And that's where the generative piece of this kind of comes out. But again, the difficulty here is f of x needs to be differentiable, it needs to be invertible, and the determinant of the Jacobian needs to be easy to figure out, and also we need to get the determinant of the inverse of the Jacobian to kind of go the other way. Another thing that we kind of need to bring up here is f needs to be bijective. In other words, there needs to be one x for every z and one z for every x. So one example of this is utilizing a cumulative distribution function. So here's our example of our mixture of Gaussian. So we can actually do the flow model with a mixture of Gaussian as well. And what we're going to do is we're just going to sum across the probability distribution of the Gaussians, directly. So you can have this flow taking the distribution and adding it. And so in this case, we just have this sort of curve, and now the z is just going to be equivalent to the x. So in this case, we're just x to z is an identical mapping because we haven't trained our distributions yet. Now what we'll do is we're going to train our distributions, and now you can see z turns into essentially a uniform distribution. And so it's possible to sample in our z space and go to any value in x space because the CDF is a monotonic function, meaning if I sample here, I have an equivalent x that it goes to below. This is kind of mathy, I know, and kind of a little bit hand-wavy, but it does work. And one of the ways that you can really do this, so you don't need to use a mixture of Gaussians. One way to do this is actually utilizing any function that has a triangular Jacobian. This is sort of beyond the scope of this lecture and class. If this is something that's interesting to you all, please let me know. This can be a lecture in of itself for sure of how to implement these things. But the results are particularly powerful. So one example of this is Glow and Glow++. And I'll just play this video and you can kind of see what's possible here, where you can interpolate an image. Once you've trained this mapping between one and another thing, you can essentially interpolate across a number of different parts of your distribution. So you can see this sort of natural interpolation between one of the author's faces to a variety of different people. I recommend you guys check out the blog post. There's a lot of really cool stuff on there. In fact, here, I can just click it really quick. Cool, lots of options. For example, you can go in here, you can upload your own image, you can change the age, right? And there are the eyes. You can make her blonde, you can give her a beard, which doesn't quite seem to work. Oh, there we go. So a very amazing kind of group way to sort of interpolate between two different things in a way that, by the way, would not be possible just with a linear interpolation, right? If we just add these things together, then it's not going to necessarily work. So highly recommend this one. Glow utilizes an invertible 1-by-1 convolution that led to really state-of-the-art results. Previous examples with real MVP and NICE utilized affine transformations, and the way you could do the affine transformation is by way of that sort of autoregressive masking. So you can ensure that half of your data is you're only doing this transformation on half your data, because if you do that, you ensure the triangular Jacobian. And if you ensure the triangular Jacobian, then the determinant of your Jacobian is simply the product of the triangular of the diagonal variables. And again, remember, we do this all in log because it's easier. And now you can, if this is just a bunch of products, then it's easy to calculate. So pretty fun stuff. So flow models are pretty powerful. Looks like I have two of the same thing. Cool. So now let's move into going back to this sort of map. We've now explored the explicit density and the tractable density part of that. Now let's talk a little bit about approximate density. We're going to skip Markov chain, but let's talk a little bit about the general idea behind the approximate density models. So say we have this intractable density function such that we take we make equivalent this is also for continuous data. Our probability distribution of x is given by essentially every probability of z times every probability of x given z. So this is just Bayes' rule, and we're basically splitting it up such that for every z that we may see, we're multiplying that by the probability of x given that z. This is sort of a kind of a way to think about an encoder-decoder model. So in the concept of encoder-decoder, or what's called an autoencoder, right? We take this input value x and we plug it into an encoder network, and that gives us this variable z. And now from z, we want to decode it back into x reconstructed, and now we can kind of figure out what the reconstruction loss is by way of MSE, or there's total variation, or a number of other ways to do this. Now the problem is with this is we don't know what the space of z is or how to parameterize it. So if we do this kind of naively, we're just going to get a value of z. We can't move in z, right? We're going to take some x, we're going to run it through our encoder, we're going to get a z, and if we try to perturb that, we're just going to get garbage on the other side. It's not going to necessarily make any sense. And so what we want to do is we want to maximize x by way of having kind of some prior distribution for z in this case. But if we do that in this particular part of this here, like this is what this is doing, right? We want to parameterize the distribution of z, but this is intractable. Like, how do we figure that out? That's not necessarily something we can do. So approximate density function models try to kind of overcome this by approximating this particular portion of the equation. So let's kind of talk a little bit about that. And for better or worse, I'm going to warn you, this is like the mathy part. And it's going to get very mathy very quickly, but stay with me, right? So if we're looking at the data likelihood of p theta of px is equal to this integral of p of z times p of x given z, right? Then the respective posterior densities, which means z given a respective x, right? So if we know x and we want to figure out the distribution of z, just by way of Bayes' rule, is going to be equal to this probability of x of z times the probability of z, just what we have up here, divided by this probability of x. But this is still intractable, right? Like we don't know probability of x. That's what we're trying to maximize in the first place. Maybe we kind of know this probability of x given z, but how do we say we have this variable of z? But we also don't really know this probability of z. So this is all kind of intractable. So what the solution is we're going to try to then define these two probability distributions, essentially the posterior and the prior, by their own respective networks. So we're going to have a p parameterized by theta of x given z. Then we're going to have a q parameterized by phi of z given x. Then we can approximate the posterior and derive a lower bound on the likelihood, which we'll talk about in just a minute. This is the mathy part, I'm warning you. But before we get into that, let's talk a little bit about that, which is if we can determine sort of a lower bound on the posterior, meaning the probability of z given a particular x, then now we have a compressed version of the input. right? So we have this sort of latent vector z. Now we know that z is on some kind of probability distribution of its own, right? So we'll talk about how we do that, right? But if we can do that, right, now we know that this exists in some kind of like latent space, right? And then we use that latent space to reconstruct that using this decoder network. Um, then we can get this reconstructed input, and now we can sort of create some way to determine an objective function for each respective part of the encoder and the decoder, right? And so this is the overall architecture of a variational autoencoder. You take the x, and using a particular parameterized mean and standard deviation, we encode that into a latent vector, right? So you can see here, in this case, z is equal to this mu plus um, the standard deviation times this value of epsilon, and epsilon is just sampled from a normal distribution. You can also use a uniform distribution. It really doesn't matter. And then now we have this sample latent vector. So we're basically taking the mean and kind of moving about it by way of the standard deviation, and we're learning the mean again by maximizing this q of theta of q of phi. And q of phi is attempting to maximize, we're going to derive a lower bound for that posterior density, and which we'll talk about in the next slide. So bear with me, the math is about to hit us right in the face. But this is, the idea here is we're trying to match this encoding to this decoding, and it's not that different than this previous encoder-decoder, except instead of doing just this, loss of the target and minus the input, we're doing so in a way that's trying to actually determine and maximize the likelihood of our particular input. Cool. So let me walk through this math a little bit, because I think it's important for to really understand what's going on here. So again, we start off with this probability of x is equal to the probability of z with theta times the probability of x given z dz. The way we approach this now is we take the logarithm of this probability of x, and we're going to make that equal to the expected value of the logarithm of p of x. Now this is no different, by the way, than just our maximum likelihood parameters, right? We're just applying this thing here, but we're trying to say the expected value is going to be based on this z that we're drawing out of this q. So this is just talking about this encoder-decoder architecture, right? We're saying we're going to draw a z out of this q decoder, this encoder thing. So we're going to encode our x, right? We're going to get some z out of this distribution, which we'll talk about in a second. And then, based on that z, we're trying to maximize the probability of the input x. And so now, this is just Bayes' rule. We take probability of x and we apply this z distribution to it, and that just results in the p of x given z times probability of z divided by probability of z given x. This is just Bayes' rule, and you can kind of see this popping out. Now we multiply that by just a constant, right? We take this probability of z given x with this q network, right? Again, we're talking about drawing z out of that network. We just multiply that. That's just equal to 1, so we can do that, right? Now, with using the log value, like the multiplicative values of log and so on, we break this up into these 3 different parameters. So here, we're taking log of probability of x given z, p xz, right? And you can see that's just the expected value here. And we're subtracting from it, we're taking this top q value divided by p. So we have it here, and then we have the same thing with this bottom q and this top p. Sorry, that's over here. We're subtracting it because we've flipped it, right? So now we have this e of z log p x given z minus expected value of the q z given x divided by p of z plus this expected value of log of q divided by p. Now, there's this idea called the divergence between 2 probability distributions, the KL divergence or the Kohlberg, I forget the name. Let me remember. Okay, Kullback-Leibler. I always forget the name of it. The Kullback-Leibler divergence, which is just simply defined as the expectation of log of Q over P, essentially. This is also equal to the sum of Q times log of Q over P, but either way, this is the form that we're going to use here because you can see that this is directly equivalent to the Kullback-Leibler divergence between Q and P, and here the Kullback-Leibler divergence between Q and P of Z with no conditionals. So here, one thing that you need to know about the divergence, the KL divergence, is that it's always positive, right? The KL divergence tries to determine what's the distance, what's the difference between two probability distributions, and it can never be negative. It's just not possible, right? And remember, this is just equal. This whole thing is still equal to log probability of our input, right? So we're trying to maximize this. So given that this is always going to be positive, we just don't care, right? This is always going to be positive. Maybe it's going to get closer to 0, but we don't care. So this can go away. And really our distribution. So what this means is we don't care what the relationship is between our encoder distribution and our decoder distributions, which makes sense, right? Because the way that our encoder and our decoder works really shouldn't matter. They shouldn't affect each other as long as we're getting a valuable Z, latent variable mapping, and a valuable X reconstruction. So this kind of intuitively makes sense. So here we just have the expected value of the probability of X given Z. So we want to maximize this, right? Given any Z, we want to maximize the likelihood that the X input came from that Z, which is kind of cool. So this basically encodes the value of our encoder network. Remember, let's go back a little bit. Here you can see Q is our encoder and P is our decoder. Sorry, I said encoder. We're trying to maximize the likelihood of our decoder reconstructing X from this sort of Z. Now here is this interesting value. So again, the divergence, the Kullback-Leibler divergence is always positive. So we want to minimize this. We want to get this down to as low as possible. And all this is saying is that we would like to essentially reduce the distance between our decoder our encoder and the probability of a given Z. And because we kind of know this, we know the distribution of Z, right? This kind of breaks down to a very nice little objective function where we're trying to maximize this probability and minimize the divergence between our between this way of our input to our latent variable. Cool. I know it's a lot of math, but this is essentially the variational lower bound. What we're doing is we're essentially determining the lower bound of our we're trying to hold on. Sorry about that. Oops, went too far. So one way to think about this is as a kind of lower bound. So the divergence is the lower bound on our ability to maximize this probability distribution of X given a particular Z. So you can kind of think about this as DKL as the KL divergence of our encoder network to our latent space goes to 0. We are essentially matching this expected value 100%. So as we get closer, we get this lower and lower, this becomes closer and closer to our true probability of that X came from our data. So that's what we're trying to maximize. Essentially, I can't get any bigger than this, right? We can't get any bigger than that. And so this acts as this lower bound to that. There's a lot of interesting overlap here with mutual information. So if you're familiar with mutual information, the mutual information between two variables X and Z is essentially equal to the entropy of X minus the entropy of X given Z, and it tends to look very similar to this particular form. So it's very much like we're trying to maximize the mutual information between this variable x and this variable z, and z is coming from a prior distribution of some kind. But this is actually pretty easy to do in practice. We can determine this value, we can kind of determine this directly by sampling. And the determinant of this is relatively easy and tractable to calculate because this is just a neural network or a mixture of Gaussians, as we'll talk about in a minute. And the same is true of this Kullback divergence, as we can see up here, right? In this case, the divergence between two Gaussians is also tractable. So let's talk about the actual mechanics here, and you can see we're just using mixture of Gaussians for these levels, and we're just applying these things to this network to calculate this mean and sigma, which then gives us this z given x, given this normal distribution, and vice versa to get x. And this is actually pretty easy to do. So the KL divergence between the prior and the Q network is used as a loss here. So we can parameterize all these things given like a neural network. Oop, let me move myself here a little bit. So yeah, it's very heavy math, but leads to a lot of very important realizations about how these unsupervised networks are working, where you're basically trying to learn this sort of latent representation. One of the reasons that we want this latent representation and how this is different, by the way, for example, from flow, is in this case our z does not have to have the same dimensionality as our x input. So in this case, we could even have like a univariate z, right, where you have just a number from 0, like just like a one value number that encodes your whole thing. And if you do have a sort of understandable space, meaning a space that that is constrained in dimension, now you can start to explore that manifold. And by manifold, I just mean the multivariate space that Z occupies, right? Again, remember that Z is essentially based on some kind of distribution, and so once we've learned these encoder and decoder networks, we can then drop the encoder network and only use the decoder network and plug in values of z from our input from that prior distribution, be it a normal or a uniform or whatever else we wanted to use. And you can kind of see this very interesting results. So on the left, this is the output of a VAE. Now, we're not looking at particularly state-of-the-art results here, but the VAE is a good way to think about this first, and we'll talk about how this has been turned into very state-of-the-art results just recently. And now you can see this very nice parameterization of our Z latent space, where it can go from 1, now it's turning more into a 7. As we go down, it turns into a 9. And you can kind of map out this latent space and kind of is understandable. More interesting than numbers, which don't have much kind of semantic meaning, a 1 and a 7 is more of a construct. In this case, you can kind of see a person's face, and this person's face is actually changing pose as we explore the latent space. So over here they're looking left, over here they're looking more to the right. And you can kind of so you can imagine using this, for example, for an avatar or for a way to sort of reconstruct somebody's face in different poses and different kind of combinations. So this is a very interesting thing to do. Oop. I guess I didn't change the text at the bottom. Sorry about that. That's just not important. So not to kind of go too deeply into it in this lecture, but VQ-VAE is a recent approach to VAEs. VQ stands for vector quantized, and this is an approach to kind of making sense of the latent space in a more quantized way. What they do is they sort of try to focus on particular centroids in a discrete space, which allows for better sampling around modes of interest. And this can actually be superior to GANs in some cases. The GANs are not super good at realizing diverse results. As you can see on the right here in Big GAN, a lot of the images have trouble with goldfish, and you get a lot of these sort of goldfish-looking blobs and shapes, but they're not particularly great, in terms of individual samples, but overall they're okay. Also in the ostrich example, you can see a lot of very similar images, ostriches from a particular vantage point, whereas the VQ-VAE approach has a much better does a much better job of sort of representing a variety of different samples, different background colors, different arrangements, right? Close up, far away, that kind of thing. And in the case of the VQVAE, you even have situations where like this ostrich, you're right up close to it, right? And creating much more varied types of samples because you're able to sort of explore the different modes of your data set. Where, as we'll talk about GANs in a minute, GANs tend to suffer from this particular problem of what's called mode collapse. And we won't talk too much about that in this lecture, but what ends up happening is a lot of times GANs seem to sort of focus on a particular set of things in the data set and produce those particularly well, but are not able to sort of generalize between different modes. And by modes, I mean sort of concentrations of interesting and valuable points in the space, right? Because when we talk about this latent space that we're mapping to, the latent space is everywhere, and there are a lot of samples in here that don't make any sense. Like right here between 3 and 4, there's a sort of 5-ish, 8-ish, I don't know, right? Like if we could sort of instead focus on this area where there's numbers, and focus on areas of latent space that are more interesting and kind of really hone in there, it's a form of rejection or a form of importance sampling in a way, then we can result in much better outcomes. So it's a different, it's a very deep subject, and I encourage you all to check it out. If somebody wants to implement a VQVAE for your final project, I will guarantee a perfect grade because that's a very cool thing to do. So, okay, did somebody say GAN? We kind of accidentally fell into that. So for the rest of the lecture, we'll talk a little bit about GANs, but GANs, and I do recommend reading this paper. The Goodfellow paper from 2014 is a very fun read. GANs are a particularly intuitive concept that are very easy to implement. In fact, the story goes that Ian Goodfellow was out drinking with his friends and was arguing with one of them that this is possible. Nobody believed him, and he went home a bit inebriated and implemented in one night. And then so, just a couple of drinks led to the complete, direction of the entire industry for 6 years since. But either way, the big kind of thing about GANs is that they don't deal with max likelihood at all. In fact, they don't really try to model a particular distribution directly. The idea behind it is you have this two-player game. It's like a video game, right? One network is generating examples, generating images, or generating data, and then the other network is trying to determine whether or not that data is fake or real. And so the discriminator the discriminator network is being trained both on real and fake images that are coming out of the generator. And this is just a supervised classification, right, of yes or no, right? You know which images are real, and you know which images aren't real, because the real data set is the data set you're giving it, right? That's your target data set, the thing you want it to look like. And the fake images you also know, right? The generator then receives loss from the discriminator, whether or not it's able to trick the discriminator, and then kind of changes its parameters and tries to produce better and better data. And what ultimately happens, this is what's called a minimax game, right? Where one network is trying to maximize the loss while the other network is trying to minimize the loss. And ultimately, if you do this well, you get to what's called a Nash equilibrium, where an improvement in one player results in a lockstep improvement of the other. And so you kind of maintain this sort of perfect balance. And the ultimate sort of result is the discriminator has a 50% accuracy in terms of whether or not a particular image is real or not real. So you've completely sort of tricked it. So in this case, the architectures you can see, again, highly recommend checking out the CS231 slides on this. It's a very good set of slides. It's a really good video lecture as well that you can check out. But given a network, it's given a random noise latent. So we do talk about latents here. The noise is sampled from some distribution, just like we've been talking about this entire time. The generator outputs some kind of images. Now we have a real image from a training set and the fake images, and we try to train the discriminator to determine whether it's fake or real. The resulting loss is calculated, as you can see here. So given X drawn from our real data, we, try to maximize the expected value of the discriminator correctly calculating 1, so 1 means it's a real in this case. Then we add to that given z pulled out of the probability of z, which is a prior noise, so it's like Gaussian or normal or whatever. Now we basically try to minimize the fact that whether or not the discriminators are able to determine that it's fake or not. So if the discriminator finds that it's 1, that means we lost. So we don't get 1. But if the discriminator determines that this is fake, then this value becomes 1 log 1, and then we add 1 to our loss. So this is sort of what's called the minimax loss for the GAN minimax loss. And you can kind of see here that in the ideal scenario where D is equal to sort of, it thinks that all the values that the generator is producing are real, but it also can say all the values from the real data set are real, right? Then we essentially have like a 50% on this loss if you take the expected value of it. So it's a surprisingly simple algorithm, but it can get quite tricky. You can see that you want to sort of, how do you just update the discriminator versus the generator? Like, do you do it at the same time? You can imagine the situation where the discriminator can sort of choke out the generator, right? If the discriminator is too good at determining whether or not images are fake or real on the start, then the generator doesn't really have a chance to catch up, and will just not get very much signal from this, right? Because if the error here, right, the portion of the gradient that is applied to the generator network comes out of this second thing. So if this is always 0, then it's never going to get any signal of how to improve, right? In a way, it's like thinking about the fact that you need to win a little bit to figure out how to win even more. If you're losing all the time, then you're never going to figure out how to maybe get a leg up. And so the discriminator kind of has to chill out if you can do it. There's a few ways to do this. One way, for example, is to, instead of minimizing this, instead of doing the mini-max loss, you maximize this, and then you also maximize that. So you're trying to maximize the likelihood that the discriminator is wrong versus minimize the likelihood that the discriminator is wrong. Yeah, as you can see here, this is sort of the case where for the generator, you're just trying to maximize this particular thing, this improved objective. There's other ways too. It's like the GAN paper that originally kind of came out. It's finicky. It suffers from what's called mode collapse. There are other approaches to GAN training which are a bit out of scope here, but I'll talk a little bit about some of the other GANs, because since this paper came out, it's just been an explosion, a Cambrian GAN explosion, if you will. And so let's kind of go through them, but let me first show you the really earlier results of GANs. So what's notable about this this was out of the first paper, and this is back in 2014 when the paper first came out. You can see these images, like on the right, the yellow images are the real images. And you can see that these generated images are, they're black and white, they're small resolution, but they're quite good. In particular, in the MNIST data set, you can see how crisp and how really good these samples are, especially if you compare it to the VAE, right? VAE, you have a couple of good samples, but a lot of them are blurry. And so you'd have to kind of look through you'd have to find the examples you care about in this case. But here, every sample is a good sample, and you're sort of guaranteed this to be true because the discriminator is going to ensure that the generator is outputting samples that we really care about. Now, there's a sort of double-edged sword here, as we saw here, right? The GAN gets very good at generating particular samples that we're interested in, but only that. It's not able to sort of deal with variability, which we'll talk about as well. There's a new form of GANs that sort of dealt with this as well. But it's quite good, but early. And then, in 2016, Radford applied convolutional neural networks to GANs, and now we're starting to see images that are color. The computation has gone up quite a lot, and it looks much better. And then Arjovsky, sorry, I can never pronounce the name, kind of came about with what's called WGAN, or the Wasserstein GAN. The Wasserstein GAN is a very notable improvement in the sort of GAN technology, I'd argue, because it applies what's called the Earth mover distance, or the Wasserstein distance, which leverages understanding in terms of the KL divergence is what we talked about with the VAE. There's a mathematical sort of exploration of the GAN loss, which demonstrates that it's a version of the Jensen-Shannon divergence. And both in the case of the Jensen-Shannon divergence and the KL divergence, what you're doing is you're trying to figure out how much your distributions are overlapping. And the problem is when you have distributions that say don't overlap at all, you've got sort of nothing there. And so the Jensen-Shannon divergence deals with this a little bit better, so that when you have two distributions that don't overlap at all, you don't get this sort of nasty mess, right? In the case of for example, the KL divergence, you have that P over Q. Well, if Q is 0, then you've got infinite. So the KL divergence blows up relatively quickly. Whereas if you do the Jensen-Shannon divergence, you end up getting this sort of value of 2 log 2 when you're in an area where the two don't the thing. So while GANs are better than VAEs in that sense, because they're using the Jensen-Shannon divergence, they're worse because of the fact that they're still dealing with this overlap. And what that overlap does is it leads to the situation of mode collapse, right? Where you have these two distributions, but they tend to sort of kind of seek out the mode of the maximum mode. So you have this distribution and it tries to match, and if there's a big hump here and a small little island here, it's going to find the big hump. It's not going to ever find the small island. And if you have a number of different modes, it's going to sort of not find those. And so that's a problem with that. Now, the WGAN, the Wasserstein GAN approach, uses the Earth mover, and the Earth mover distance, the Wasserstein distance, attempts to sort of deal not with the overlap, but with the distance between. So sort of like the horizontal spacing between these things. It actually utilizes, the math gets a little bit hairy and kind of is beyond the scope of this, but it uses a particular duality, or I always forget the name of it, one second. The Kantorowicz-Rubinstein duality. So Kantorowicz-Rubinstein duality kind of holds that the Wasserstein distance is equivalent to the expected value of the two probability distributions, given some limitations on those distributions, and that limitation being what's called the Lipschitz continuity, which really just talks about how sort of what's the slope looking like of this. If this is interesting, I recommend reading the paper. It's a lot of math just to get to the fact that you're essentially going to clip the weights of your network. But what it does do is it results in significantly better results in terms of exploring the possible different value, the possible different, it improves the variety of your samples quite substantially. As you can see, there's a lot more variety, and we get better bedrooms and things like that, and much more believable so. So WGAN really improved this thing, and also it really reduced, remember we talked about how the discriminator can sort of snuff out the generator. In this case, the discriminator gets moved into what's called a critic, and the critic is now outputting a value that versus a yes or no. And so because it's a continuous value, it's much easier to sort of shift. And so it's much harder to get to that situation where your generator no longer is training because your discriminator is too good. So that's one of the really big improvements that was made with the Wasserstein GAN. And Wasserstein sees a lot of applications throughout. There's even a Wasserstein autoencoder, which is something I'm about to check out. And you even see Wasserstein pop up in like segment tracing. There's a paper that just came out, for example, in segment tracing, which is an approach to path tracing for SDFs, which allows you to do much better, much faster path tracing for SDFs using, again, the Lipschitz continuity, because you can sort of figure out where you want to go, and it doesn't slow down near sort of high curvature regions. So very cool, very cool. Again, highly recommend reading this paper. And then let's kind of move on to sort of the last GAN slide, and we're almost through this. I know this has been a heavy lecture compared to the other ones. It's a lot of stuff. But a lot of GANs have kind of come. So like, for example, the cycle GAN. Cycle GAN uses a really interesting architecture where it sort of does this cyclical thing and just keeps going until it gets to something that is really believable. I'm not too familiar with the cycle GAN architecture. One of the really exciting improvements that have been made with GANs is style GAN, which has sort of led to a lot of those very sort of photorealistic images you can see here in this image. These are all fake people. And what StyleGAN does is it sort of uses a generator to produce a latent space and then out of that latent space are pulled out these styles, which are then produced into this image. I haven't read this paper in some time, but it does. It really kind of pushed the state of the art up significantly. Another really cool paper, Pix to Pix by Isola 2018. What's really interesting about Pix to Pix, which I think is very, very valuable for games in particular, you have a lot of control over the output. Like, for example, this can be used for aerial images to map images without having to sort of calculate all these things. You can take things and make them from day to night. You can plug in sketches and output images, and the way that this is done is by conditioning the GAN. So if you remember the architecture here is you have a random noise. So to this noise, you're also adding a conditional value. And you also are conditioning your real images, and that way your generator learns to produce particular images that the discriminator thinks is correct given sets of conditions. And once you do that, then you can add in and you can plug in whatever conditional you want. So you can now start to draw cats and make a cat generator. You can make a facade generator. And this is one of those applications where this is very, very valuable for games, right? Say you want to do this for texture design or for image, like create a city procedurally. There's a lot of really cool applications here. And by the way, Pix to Pix and this sort of conditional GAN thing, we didn't talk about style transfer too much. Maybe I'll set that up. But there's a big sort of subject in style transfer and being able to do similar things as well in like a single shot capacity. So the last thing I'll talk about is game GAN. This is a really notable paper to me. This utilizes the GAN design along with like a dynamics engine and memory component. These are all neural networks. And with what it did is actually you plug in a game to it and it will learn the game. So this will eventually output a game, and you can you plug in the game, and in the beginning, these images that are coming in are coming from the actual game. And then over time, you unplug the game, and now this neural network is able to play Pong, to let you play Pong, and to do whatever. So it's just taking input. And this memory module is actually a neural Turing machine. The dynamics engine tends to be some kind of MLP or some other thing like that. Rendering engine is just a GAN in architecture, as you can see. And this architecture allows you to sort of learn a game. And this was done with Pac-Man. It was also done with like Doom, although Doom didn't come out quite as well. But early, very, very promising results. So imagine a game that is entirely being provided to you by a machine learning network. I think that's not that far down the road, actually. So yeah, that's about it for this lecture on a lot of different generative models. Next time we'll talk about reinforcement learning, or start to as well. If you have any questions about any of the things talked about in this lecture, please let me know. I'm happy to spend more time creating more lectures on this stuff, or digging deeper into the material. I know a lot of it was sort of quick and high level. Obviously, almost every slide of this particular talk could be a lecture in of itself. And so if there is any interest in any of those things, please let me know. In fact, if it's of interest to set up a lecture just on a particular GAN and how to implement it from start to finish, could also set something up like that. So please let me know what you're interested in. Otherwise, we'll move into reinforcement learning next, which is a way to apply both supervised and unsupervised techniques to this problem of how do you get an agent that is now collecting its own data in a sort of environment. So yeah, that's about it for now. Thanks for listening.